Good afternoon and welcome to another Royal Astronomical Society's online public talk. Hello, I am Lucinda Offer, Education Outreach and Events Officer for the Royal Astronomical Society. Our organization advocates for astronomy, geophysics, and space science in the UK since 1820. And if you're interested in astronomy and geophysics and enjoy our lectures, then you might be interested in the Friends of the RAS membership program. Friends of the RAS have access to 6 to 8 additional talks like this one every year, as well as discounted rates on our astronomy and geophysics magazine, and pandemic permitting, use of our incredible historic library. Membership is £40 for the year. Please visit our website, ras.ac.uk, for more information. Today, I'm excited to introduce to you our public lecture guest speaker, Dr. Margarita Segou, who will speak with us about earthquakes and the work of seismologists over the last decade to deliver the best mathematical, physics-inspired models to simulate their continuous chatter and aftershocks. Scientists want to learn how earthquakes evolve in preparation for how and when the big one will hit. Dr. Segou is an earthquake seismologist at the British Geological Survey in the Lyell Centre, Edinburgh. Her accomplishments include applying state-of-the-art forecast models to estimate aftershock, spatial, and temporal distributions for major earthquake sequences around the world. She has demonstrated how long-term secular stresses drive short-term aftershock ruptures and revealed under which conditions earthquake model predictions may be useful. She has studied and worked in California, France, and Greece, analyzing almost any major earthquake catastrophe from 1989. She has delivered invited lectures in research institutes in the US, UK, EU, Japan, Turkey, and Switzerland. Her work on the grounds of the Central Apennines immediately after the 2016 Amatrice earthquake in Italy was acknowledged by the UK and Italian governments as a paradigm of international scientific collaboration. A quick reminder that there will be a Q&A after the talk, so please get your questions ready. There are places to post your questions for our speaker in the Q&A box on Zoom and on YouTube in the chat box. Thank you, Dr. Segou, for being with us today. On to you.
Hello. I would like to thank the Royal Astronomical Society for their invitation to give one of their public lectures and have the chance to interact with all of you today. So the subject of today's talk is about earthquakes. So earthquakes correspond to one of the most disastrous natural phenomena with farthest predictability when compared to floods and fires. In the talk today, we're going to take a journey around the world to understand what the best earthquake forecast looks like and why earthquakes are so difficult to predict. Towards the end of the talk, I'm going to talk about how artificial intelligence uncovers these previously unhidden earthquakes around the world. The talk will focus on how earthquakes interact in close and distant ranges and how scientists are tracking this chatter across the globe. Earthquakes may occur anywhere across the world, but it is the tectonic plate boundaries shown in this figure as red lines, where the majority of large magnitude earthquakes occur. Here we see the epicenters of around 4,000 earthquakes with magnitude larger than 6.5 that occurred after 1900. Most destructive earthquakes are found inland, and those can cause widespread damages in modern structures, in cultural heritage sites, and cause population to be relocated. But also it is the earthquakes offshore, that they happen in the sea, that under specific conditions can cause tsunamis that can be equally destructive. Of course, every country does not share the same exposure to earthquake risk. A magnitude 4 occurs in UK on average every 30 years, whereas every 30 days or so, the Californians are feeling a light jolt. In Europe, Italy and Greece are practically under the earthquake weather, since every 8 to 10 years, a magnitude 6 and above earthquake happens. Perhaps one of the earthquakes that it's still very vivid in people's memory is the 2011 magnitude 9 Tohoku Oki earthquake that hit the eastern shores of Japan. The earthquake caused 16,000 lives to be lost, 300 million pounds in damages, and a nuclear accident in Fukushima power plant. The offshore megathrust fault that marked the tectonic plate contact that day released accumulated energy equals to 30,000 Hiroshima-type bombs. Similarly destructive earthquakes happen in other offshore subduction zones in the world, including the Mediterranean one in the past. We track these mega disasters of the past by looking at depositional signatures in the ocean environment and along our coasts, and analyzing archaeological remains. Luckily, it is the intermediate-sized earthquakes that happen on land they are more frequent. This is a known seismological principle known as frequency magnitude distribution that postulates for every magnitude 7 earthquake, we have 10 magnitude 6. Shallow earthquakes on land happen on the topmost 10 kilometers of the Earth crust and cause extensive damages. Here is a figure, a photo from my personal archive from the Amatrice village that was hit by an earthquake on August 2016. You see that the tower clock here, time has stopped, but it is with the help of metal braces that continues to stand on the ground today. This is not the most damaging earthquake, but definitely it is one of the most recent ones. So Italy has a population of over 60 million, and within the last decade, more than 100,000 people are being affected by earthquakes, whereas just less than 20,000 are being affected by floods. If we take a look here on the right, we see in color the 2016 earthquake sequence that started with the Amatrice earthquake on August 2016. But also we see further to the south the L'Aquila earthquake sequence that hit the region in 2009, and further to the north, the Colfiorito earthquake sequence back from 1997. If you imagine that you are in January 2016, few months before Amatrice earthquake occurs, you would see that this place here is void of any earthquakes. This is another known principle in seismology known as the seismic gap hypothesis. So let's now see what an earthquake sequence looks like. So an earthquake sequence is a tight cluster of earthquakes that happen closely in time and space. In the particular case, the earthquake sequence started with the Amatrice earthquake on August, and it was followed by further seismicity in the north part with 2 magnitude above 5 that occurred near the Viso village within few hours. 3 days later, the 6.5 Norcia event, further to the north, marked the largest magnitude to date of the sequence. Few months after, seismicity moved to the south, near the village of Campotosto, where 4 events larger than magnitude 5 hit the area within few hours. From the very first days of the Amatrice sequence, an international team of scientists from Italy and UK have deployed together a temporary monitoring seismic network to better record the strong ground shaking. This operating network had more than 150 stations and remained active for 1 year until it was lifted on August 2017. So the first year of research usually has different activities, from summer deployment to check whether the instruments are operating fine under snow, gathering around the dinner table after very long days, documenting the pattern of damages that we see on land, and sometimes training our PhD students on the ground. Here you're going to watch and hear what my PhD student back then, now postdoctoral researcher Simone Mancini, tells us from downtown Amatrice about what he thought his work would be like the first week after the earthquake.
So we are in Amatrice downtown now, where much of the damage occurred after the 24 August magnitude 6 earthquake. And around here, we have our network deployed after the 24 of August, from the north, Norcia, to the south, to Campotosto. What I will be doing and what I'm doing now is to create models that can result in reliable forecasts, since this is a great example of how the damage was distributed in space and in time. So creating forecast models based on the physics of earthquake will be a major challenge in the next year and decades.
So few months after this visit in Amatrice village on January 2017, we had 4 earthquakes with magnitude larger than 5 that hit the southern region near the second largest dam in Europe, the Campotosto Dam. Here is the preliminary information as delivered to the public from INGV, which is the responsible institute in Italy for delivering earthquake information. On the back, you see a photo from the artificial lake of Campotosto Dam covered in snow. So the moment that the earthquakes hit this southern region, and decision by officials was taken to drain the artificial lake to prevent further damages occurring on the dam. However, we saw villages in our visits around the Campotosto Lake, as shown here, the Campotosto village, that residential buildings suffered 80 to 90% of very heavy damages. Of course, we saw extended damages, but something promising to see was that very simple reinforcement actions that were taken during the summer prevented cultural heritage sites, such as this church that you see here, being preserved. So we see here that the church at the entrance of Amatrice village was supported by wooden pillars and metal braces along its perimeter, and it's still holding up today very well. So why it's so difficult to predict earthquakes? I mean, by now we know that predicting deterministically where the next future large earthquake will happen and what the magnitude would be is impossible. But also, it seems very difficult to see how each earthquake sequence will evolve at the time of the first main shock. So let's go on a global tour around the world to understand better the different patterns that characterize every sequence. So here you see the 2009 L'Aquila sequence. L'Aquila earthquake occurred in early April 2009 with magnitude 6.3 hitting L'Aquila city, and small magnitude activity was felt in the area the days before. This earthquake caused different societal responses ranging from what an earthquake forecast should be like to legal actions being taken against scientists. However, small magnitude seismicity felt by people does not always have a prognostic value, since many times small magnitude earthquakes do not necessarily lead to catastrophic events. However, in 2016, as you will see here, the southern Kyushu island in Japan was hit by a 6.2 event, which was followed a few hours after by a magnitude 7. Next to it, you will see the 2014 Napa earthquake that hit Northern California, which was followed by really small magnitude activity that lasted only a few months. However, that first day, scientists were really worrying and investigating whether nearby faults will be activated in the region. In 2010, 2011, New Zealand was hit by an earthquake in September with magnitude 7.2, hitting the western tip of Darfield Fault, which was previously unmapped. Intense aftershock seismicity followed, and seismicity migrated to the east, hitting on January just beneath the city center of Christchurch with a magnitude 6.3. That earthquake devastated the city center, people relocated, and businesses closed for many years to come. So from all of these paradigms, it is clear that seismologists cannot base their advice on their empirical knowledge. We simply do not know what will happen next. So we develop mathematical models that can explain and describe what future seismicity would look like. So models, such as the ones that I just mentioned, use preliminary information. So the moment an earthquake hits around the globe, we have within minutes some of the first descriptors. We are firstly interested about the magnitude of the quake and where obviously this has happened, as the latest earthquakes webpage of the US Geological Survey informs us. Another piece of useful information is ground shaking, which can range from severe, near the earthquake, feeling like your building is shaking, or light shaking, like a truck is just passing by outside of your window. The second thing which is interesting is regional information. So people are asking, has this happened again in the region? Many times the answer is that yes, it has happened before, but it might be during our lifetime, so we have a memory, or it might have happened during historical times. Another piece of information is the recorded testimonies from people on the ground describing how the shaking was felt in the area. All these witness accounts and testimonies are gathered and they're available for you to read in the Did You Feel It webpage. In modern times, we are interested about an on-the-fly estimate of the losses due to the quake. Losses could be seen as estimated fatalities or as estimated economic losses. And then we have all sorts of scientific information, such as the depth where the earthquake occurred, or what kind of fault moved and what was the sense of slip, and a description of the fault on the Earth's sphere. But it was not always the time that all this available information was possible within minutes after a quake. In fact, it was not so long ago that instead of having hundreds of stations around the globe monitoring how the ground shakes, we only had a few. And back then, seismology was not even a distinct scientific discipline. But it was not so long ago. It was just back in 1906 when San Francisco earthquake hit Northern California. Back then, a single seismogram, as recorded in Albany in the east coast of US, made the front page of the New York Times. Here you see a very famous photo of the City Hall of San Francisco being destroyed. Fires were widespread in the city and caused the devastation of the major buildings and facilities around the city. This gave rise to the success story of Los Angeles further to the south. As in modern times, where witness testimonies from celebrities are circulating the globe and get the interest of the press and the media once an earthquake happens, we had similar representations back in 1906. Here is something printed in the London sketch showing how the opera tenor Caruso, who was at the time in San Francisco and gave a performance of Carmen in San Francisco Opera just the day before, actually fled California to safety to his wife and son in Italy once the earthquake stopped. Seismology has made quite a progress the last 100 years. So now we are able to quantify the future aftershock occurrences and quantify where large earthquakes should be expected. Here you see the outcomes of such a research project called USERV, explaining and describing the probability of large earthquakes to happen in California for the next 30 years. Of course, in bright red is the infamous San Andreas system, but sometimes nature can surprise us and can give us earthquakes where they're least expected, like the 2019 Ridgecrest 7.2 earthquake. So now let's see the basic seismological principles that we use in order to estimate where future occurrences will happen. The theory of stress transfer is known from the early works of Charles Richter, which is considered to be the modern father of seismology. According to the stress transfer theory, after the occurrence of a large earthquake, the stress equilibrium in the crust is changed so that some of the neighboring faults are being brought closer to failure. Therefore, it is more likely there to have aftershocks, and some other faults are further inhibited, making them less likely, to host earthquakes. Seismologists are quantifying these stress influences by estimating a parameter called stress changes on nearby faults every time a large earthquake happens. Here we see such an example from stress change estimation from a landmark earthquake in California, the 7.2 Landers earthquake. So you see here aftershocks happen in red zones where we have stress increases. And if you now look at the legend over here, you see that scientists have estimated just 0.3 bars of stress increase at maximum. So if you consider now, this is not a really important stress change value. I mean, your espresso machine, if you have a good one, operates around 20 bars. And when your boiler is at full throttle, it is around 10 bars. So it's not really that important. But scientists and seismologists in particular believe that always the crust of the earth is on an elegant equilibrium, and just a small minimal quantity of additive stresses is really needed to host aftershocks. You also see in this picture earthquakes that happen in the shadows, in the blue zones, where they're least expected. So one way to reason this is that in our effort to forecast future occurrences, scientists are oversimplifying nature. So if you take a look here, in the beginning of this sequence, we thought that faults are really single lines with single orientations. But if you see at the lower part of the figure, you see other known faults that come in different orientations, in different shapes, and different lengths. So our complex modeling tends to oversimplify nature, and at the same time, there are many things that we just don't know. So eventually, what we need from the operational point of view is having simpler models models that do not use fault information, and they're easier to implement and inform us about expected occurrences. One particular family of these models is known as epidemic type aftershock sequence. And these models treat earthquakes as an explodic epidemic over a region. These simple models are based on the assumption that no matter the magnitude, every earthquake is followed by its own aftershocks. I'm illustrating this using this diagram and the Simpson family tree, where we start with a single earthquake, producing 2 children aftershocks. And each of those children can have 2, 1, 3, or more children. Of course, the underlying assumption works well, but one thing to have in mind is that under this model, if you lose early on the family tree 1 earthquake, you lose all the branch that comes after. So this model works fine if someone knows about the existence of all earthquakes. Sometimes knowing about the existence of those earthquakes, something that in seismology we call detection, is very difficult, since our stations recording strong ground motion, sometimes they suffer from damages and power loss. So in the early hours after an earthquake, journalists usually asking, are we expecting a larger magnitude earthquake? And I think we have covered in this lecture by now that seismologists actually do not know. I mean, our empirical knowledge does not really help us towards answering that question. So we are gathering all this streaming information, and we are putting together models that could be inspired by physics or statistics or empirical knowledge. And we are trying to track the future earthquake occurrences. Here you see an example of what these models really look like in scientific practice. So in these colorful maps, every point of the grid corresponds to the expected number of aftershocks that will occur in this tiny box on the next day. So, and we make models under different assumptions. Often, which model is doing better is unclear, but what's for sure is that each model provides a useful test for a specific scientific hypothesis. We use tests, statistical tests, at the close of day to evaluate the performance of these models. We are tracking how good or how bad they are in informing us about what will happen next day. And we could see here in these colorful maps 3 kinds of behaviors. So we see, for example, blue, and earthquakes do not happen there correctly, as blue indicates low expected magnitudes, low expected number of earthquakes. We also see here red colors where we expect at least 1 earthquake to happen, and indeed earthquakes do happen there, so it's a success. And we see also bright yellow colors without any earthquakes happening. So these 3 different types of failures are intertwined in our models, and scientists are doing the best they can in putting together the best model. So what these models, aka earthquake forecasts, show? So it depends what we're asking the model to tell us about. So on the first line here, we see the simpler physics-based inspired model. So you see that the model is not really doing very well. We see a lot of yellow and blue colors, and earthquakes do happen there. And so they're not well predicted by the model. Seeing that, we have devised a more complex model here on this line. And this model pairs up the effects from large magnitude earthquakes and small magnitude earthquakes to inform us about future occurrences. And we see here that the red colors are overlaid by the dots, and the dots are where the earthquakes actually happened. So this model is doing better. On the last line, we see the EAS model, the simple model to implement. And this model does not use faults or stresses or any other data expensive parameters, but instead uses the preliminary information available within minutes. And that is the earthquake, epicenter, and their magnitude. So if you imagine that the earthquake hits a region midday anywhere in the world, and we run this model, we might have something to say on the evening news the same day. So that's pretty important. At the same time, our understanding of faults and earthquake interaction is getting better and better. So from the original representation of blue and red zones that dominated science for the last 20 years, we now pass in a more point-by-point, fault-by-fault approach. We have new ways here to represent known and unknown faults. So instead of using one single fault with one orientation, perfectly planar, we could use a group of faults that they are characterized every time for their chance to host large earthquakes the next day. And of course, illustration is very important. So instead of having one line on a map showing the fault, we are borrowing from DNA sequencing these colorful checkerboard representations to illustrate different groups of faults of different kinematic characteristics, as we say, evaluated for the probability to host future ruptures. The example here is taken from the analysis of El Mayor Cucapa earthquake, a 7.2 earthquake back in 2010 that hit the region of the US-Mexican border. By now in this lecture, we have discussed a lot about how earthquakes interact at close distances. But something very important came to our attention from studying the 1992 Landers sequence over here. So we, and by we I mean the seismological community, investigated and proved that a widespread of seismicity covered the whole Pacific Northwest, going beyond state boundaries, just after Landers seismic waves occurred. So this is a figure from the seminal work of late Dave Hill that showed the effect of this phenomenon known as dynamic triggering. Dynamic triggering occurs at remote distances when the seismic waves that they are generated at the earthquake source over here travel across the crust. From the west coast, seismic waves travel within half an hour, reaching the east coast. And within hours, they circulate the globe and eventually they die off. With modern seismic networks, we have shown now that dynamic triggering and remote dynamic triggering, to be precise, is rare, meaning that only 2 to 3% of magnitude 7+ earthquakes are connected to local dynamic triggering patterns. So this means that when an earthquake happens far away, like here, an earthquake happened in Kermadec with a magnitude 7.2, there was a widespread seismicity covering Greece for hours and days until this small magnitude seismicity due to dynamic triggering subsided. Of course, every region of the world is different. And by now we know that although this phenomenon is rare, there are regions that they are more susceptible to it, such as geothermal regions in Northern California and extensional regimes in Greece and New Zealand. Determining now a link between small magnitude regional earthquakes and occurrence of magnitude 7 earthquakes is difficult, since as you move away hours and days from the occurrence of the large event, more local effects can actually be more influential to the magnitude 5 occurrence far away. This statistically is exactly the same problem as what we see on TV recently, trying to justify thrombosis after vaccination. So if you move away from from the hour of the event, then it is very difficult to justify and describe a causal link, because many other things may have happened in between. In this very, very complex scientific environment, nowadays artificial intelligence offers new ways to describe the earthquake problem. I'm not sure, but I hope that many of you have used Shazam before. So it's many times that you listen to this song over the radio and just you cannot recall the title. And you open the Shazam app and you put your phone closer to the radio, and then the title is there on your screen. So this is how Shazam operates, using machine learning techniques underneath the app. And have you ever wondered how your Yelp review get an instantaneous number of stars? Obviously, when you write words like exciting, tasty, delicious, those words are more relevant, and they're kind of hinting the programmer that you had a great experience. So in some way, machine learning works like this for seismology. So there are some wiggles that they seem more like earthquake signals and less than, the signal from a truck passing outside of your window. So let me now illustrate to you using the Amatrice sequence example of what machine learning is doing for seismological research. So here on the left, you see an image of 370,000 earthquakes that cover the Italian countryside during the first year. And this is a result of excellent but standard practices that seismologists use in monitoring rooms to deliver the information available through the web within minutes after an earthquake occurs. We have used machine learning to detect more earthquakes and uncover the hidden earthquakes that happened in the region within this first year. And we have come up with 1.4 million events with magnitude detected close to 0, meaning that the size of the fault that actually gave this earthquake is comparable with the size of my desk, although you cannot see my desk at the moment. It is around 2 meters wide. And further on, we have come up with new ways that we are detecting similar earthquakes, and in this way we are locating where the earthquakes happened in the Earth's crust. So here on the figure on the right, it seems like someone has used a microscope and put a blood stain underneath it. And this is an exceptionally high resolution image of the earthquake system, one that it is the first time that seismologist sees that. All this research, the last 5 years, is realized from an international collaboration between UK, US, Italian, and European institutes in a program that aims to detect as much earthquakes as possible during this 1 year in the Italian countryside, and use this earthquake information to develop robust forecast models. Using this information, it is now possible to image fault structures that we haven't seen before. And if you look here, well, faults are pretty complicated structures. They can have a dip, they can be semi-planar, and they cover, most importantly, the full 10 kilometers of the Earth's crust. Also, they appear to have different sizes. And this is very important when we're trying to guess out what's the next magnitude would be. And now, before this talk comes to an end, I will be showing you a video, an animation of the seismicity that we know now happened in the Apennines in the year 2016 to 2017. You will see as the animation continues that seismicity first migrates to the north, then goes to the south. And with flashing red colors, you will see areas where earthquake activity is continuous. So this continuous chatter that I promised you to see is evident from this earthquake system representation. So let's see how this continuous chatter looks like. Well, this was all for today. This is some information of how to get in touch with me. There are many events and new research results will be shown to different conferences in the next few months. So stay tuned. And if you travel or if you experience an earthquake where you live, please go on the webpage of US or EMSC, report an earthquake, how did you feel it, and give us plenty of information to work. Thank you.
Wonderful. Thank you so much, Dr. Segu. It was fantastic hearing about earthquakes. I'm a geologist 30 some years ago, so it's been a while. I mostly went into Mars analog research, so it's kind of nice to kind of get an update on what's going on in seismology. And it sounds like, I was wondering, is this work mainly being done in Italy or is it worldwide? Is this sort of the methodology that seismologists use today?
Well, the work is always global in the sense that we are trying to study as many earthquake sequences as possible to get to some reliable and generalizable conclusions. I use the Italian experiment and the Italian research to show you what will be the results of an earthquake research if we have the best data available.
Yeah, I'm also from California, so I am very much used to going to the USGS, and we have a lot of earthquake activity there. I've been living in the UK since 2009, so over 10 years now, and I have yet to feel an earthquake. I know they happen here in the United Kingdom, but nothing like I felt living in the San Francisco Bay Area, obviously, along the San Andreas Fault, which is where we love to build very big, expensive houses on, unfortunately. So I'm very familiar with the USGS. I really, every time I'm in that area, I often do feel an earthquake, even when I'm traveling and visiting California. And I am one of those people, obviously very interested in earthquakes, who will then give feedback to the USGS. So I totally agree with you. It's really interesting. It sort of helps relieve your anxiety as well, contributing to science, to helping them understand where are you when you feel it. And that kind of leads me to one of the questions that someone asked, which is really interesting. I've never even considered this before as a geologist, but Sasha asked, How big is the epicenter actually? And I imagine it matters on several different factors, but she wants to know why or how big a region does the earthquake happen in?
Well, that's a good and very specific question. So let me explain. So the epicenter is the point in the Earth crust where the earthquake actually begins. So this is the first point that seismic waves radiate from. However, when we're talking about the magnitude 6 earthquake, this continuous slip along the fault happens across 20 kilometers. So, and this adds up obviously to the complexity of getting preliminary information out and describing with fault models how exactly the earthquake occurred.
So from your animation that you showed, it was also very interesting because you could see where it started. I'm assuming that was showing epicenter initially.
Yes.
But I saw that that graph had axes on it, but they weren't labeled. So I was wondering, how long did it take the time for all those sequences, I guess, to build?
So the animation comes from the Amatrice sequence. So it was just one sequence, and it was just 1 year. And it was a very productive sequence, I'll give you that. So the major strong large magnitude seismicity occurred over the span of the first 6 months, but this continued with smaller magnitude activity until the first year was complete. But it is not always that case. For example, when large earthquakes hit, such as the Tohoku magnitude 9, we see intense aftershock seismicity for years to come.
Wow, so you can really get a lot of data that then has to be analyzed. Well, so I'm going to get to one question from YouTube. You have some people watching you on YouTube. A viewer there asks, are there any organized plans to reinforce existing structures in poorer countries? Because you showed, I think, was it a church in Amatrice from that earthquake using low-cost methods. I don't know if you know anything about what they're doing when they rebuild those structures. Are they reinforcing them? And is it cost-effective for them to do so?
So one thing I could say is that there is a lot of interest in how poor countries would be supported in their quest for implementing scientific information to the wider benefit of the society. And there are many projects, including one that I also contribute to, that we're looking at 5 cities across the world, and we are trying to devise earthquake information, scientific information that could be used towards more sustainable lifelines and structures in those areas.
Yeah, it's because you want to also make sure they're living in safe, safe habitats, and that hopefully that didn't injure or not many people. Some people survived. There was a high casualty from that earthquake. So some of the questions from our Zoom viewers, thank you for being with us, by the way. Ross Henderson says, thank you so much, Dr. Segu, for your very informative talk. And they ask, have you any experience with the DAS, which is distributed acoustic sensing? I guess and it was published in IRIS, or maybe IRIS uses that, which uses dark fiber to predict seismic events. It's a relatively new tool in seismology, they say, and involves many citizen scientists in Western Europe and the US.
Yes, so this is one of the newer technologies used. I would say that this technology is used not to predict earthquakes, but to detect earthquakes. And this new technology might be also implementable not only on land, but also offshore. So that's a very important contribution of this new technology. But once we move away from detecting an earthquake, which means that we know its magnitude and location and where in the earth this has happened, we have to use all accumulated knowledge to develop, if you wish, forecast models that will allow us to, foresee what is going to happen next. So it's a game, it's a continuous game between people working in earthquake detection using fiber or standard methods, and people that they are working on forecast development in order to actually reach the final goal of science, which is to come up with what is going to happen next.
Yeah, absolutely. Earthquakes, affect so many. It really should involve us, which is what you're bringing up, USGS, and the contribution of giving your feedback if you've experienced one. And of course, all that data is really important for those cities to better build their buildings for. So that's really a good question and good to know. So one thing you did say there in your answer was, or in your talk, which I thought was really important, is that we cannot predict earthquakes. That's just not possible. What you're looking at with these mathematical and physical methods is what probability, I think you said. Is that correct?
Yeah, so it's exactly how science moves nowadays. And, science is also a part of the society, and society changes through the years. So in the early 70s, there was a super optimism after one or two examples that earthquake prediction will be possible deterministically. So we'll wake up one morning and we will say, we'll watch the weather, and someone will say, we anticipate an earthquake tomorrow of magnitude 7 to happen. But we now know that this is not possible. And after the 80s, the way that we handle this uncertainty and our lack of knowledge is expressing with probabilities what we think it's more likely to happen. And let me be clear, by saying what we think, I don't actually say that seismologists and science per se are expressing their opinions, rather than developing tools that are expressing what is likely to happen using all of the available information that we have once an earthquake hits.
Okay, lots of really good questions that are still part of the Q&A. We still have 8 minutes left, so I'm going to try to get through some of them or most of them as I can. So one of the questions here, Peter asks, do you have the tools or capability to allow generation of 3D maps of activity? So you showed your animation. Is that available? Maybe in a 3D form? I'm sure lots of the geophysicists and the models I've seen have been incredible. I'm sure this must exist.
Well, of course, all the models that I presented today, I presented 2D maps, but there are also 3D maps. And no matter how you describe, how you visualize the result, the forecast models are 3D mathematical models. So the depth is one parameter. And the depth is very important parameter because, if you are imagining that in the particular sequence in Amatrice, the fault was 20 kilometers long, well, the seismicity also went 15 kilometers deep. So you go as deep as you go wide. So there is your hint that you should use 3D representations to solve those equations. Yes.
I am not surprised because technology has just boomed. And absolutely what you said, it goes downwards as well. And we should really follow all the data, but we just normally focus on what's on the surface and how is it affecting us as someone who's living in a building and wanting to know, did I purchase my house in a safe space?
I hope, yes.
Yeah. Okay. Other questions here. Okay, that was great. Thank you for that, Peter. Pernille is asking. I'm not sure how familiar she is. She's asking: is there any known speed for how fast earthquake shock waves travel, or does it depend on the local terrain?
Well, it is. We know, and it is yes to the second question. So there are two basic types of waves. And the first one has the wave speed is 5.6 kilometers per second, whereas the second one and slower is around 3.5 kilometers per second. And those are the velocities of the seismic waves traveling. But as they travel through the crust, it is also very important how they are amplified or not amplified due to local geological conditions. So when we use other types of mathematical models, known as ground motion estimation models, we also account for local geological conditions to understand and estimate how much the ground will move.
Absolutely. That was an imperative to the Marina District in San Francisco, with Loma Prieta being built on landfill instead of bedrock. Yeah, absolutely important, which is why I'm always looking at geology for any places I'm choosing to live. H.C. Edward says, fascinating talk related to the question of building reinforcement. And since you're talking about buildings here, he's heard that some modern buildings, such as those in Japan, have earthquake proofing. What kind of thing helps make buildings less likely to suffer the damage from earthquakes? Are you familiar with this?
Yes, of course. So obviously, earthquakes, as we said, bring a lot of damages, and then the damages can go to millions, if not billions. So every country, especially the countries that have high exposure to earthquake risk, have national building codes, and those are laws that should be implemented at all times when a new building is developed. And of course, the standards are also varying between buildings. For example, your house will build to the normal standards, but if you're building a hospital, then this should be built to withstand even severe ground motion. So these are the major policy steps that ensure that our buildings are less likely to collapse in case of an earthquake. And those national building codes are also under continuous revision, especially again in high seismic hazard countries such as US, Italy. So this is this type of information is provided to the public.
Yeah, I actually, when I moved to England, I bought a grade 2 listed. That's kind of considered a heritage. It's a 500-year-old building in England, and even that was reinforced. So absolutely, we want to make sure that these buildings stay up, and especially if countries want to keep their heritage type buildings, they're going to have to do some retrofitting.
Well, UK doesn't actually have a national counter-seismic code because, as we said, earthquakes are rare. However, they are in many cases, if someone really wants to look for this kind of information, there are also international building codes, and there are also the Eurocode 8, which is a European building code. And then the level of standards you're going to apply actually commensurates with the historical information about earthquakes that have happened in the region and the modern seismicity. So all of this are somewhat taken into account in those building codes.
Yeah, probably my reinforcement was to keep a 200-year-old facade attached to the building and less likely for an earthquake. You're absolutely right. Okay, so I'm going to keep an open mind here with some of these questions. Actually, first we got a question from Andy. I'm going to try to understand it. He might have been asking this when you were showing the different types of models from simple to complex. And he says, if oversimplifying nature is a problem, as this could then cause a model to miss some quake events, doesn't the need to simplify models conflict with this?
Well, it also depends on what is your aim at any given moment. So, and this is where, you have this operational branch of science. And to illustrate what I say is, for example, once in 2015, we had the Nepal earthquake devastating that city. We immediately start making models to see what is going to happen next and publish our results after peer review. But if you go outside of the operational mode, where you actually need to oversimplify to get to a result faster. There are experiments that the one that I showed you results from, that they work on retrospective mode. And what this means is that we are bringing ourselves back to the day that the earthquake happened on August 24th, 2016. And we have all the available information. We have what we say the best available information. And we use all that to make the best possible forecast model. So science works in two ways. I mean, retrospective testing using best available information tries to answer this question. Is it a problem that we have oversimplified things, or is it really the problem that it's something that we do not know? As we say in science, there are known unknowns, the ones that you imagine that they're important, but you cannot solve at the moment. And most importantly, and most intriguingly, there are unknown unknowns. So there are some things that we are simply not aware of that they are important. And obviously this cannot be a part of the operational, the retrospective testing. Although this is an active region of research on how we are tracking the effects of even the things that we do not know of.
That is science, why we do science. So to look at things with open mind, and I think I want to ask the last three questions to you, kind of combine them all, because it's all about curiosity, human nature, and wondering, what is affecting earthquakes, and maybe what I learned at university are different from, what the general public considers or thinks about. And so these three questions are asking about other effects on either causing an earthquake or perpetuating an earthquake, or what other things might it affect. So someone asks, do the tidal forces from the moon perpetuate these sequences or precipitate earthquakes? Someone else asks, can a major earthquake, if it's big enough, affect the Earth's axis? And someone else asks, what do you think about the theory of earthquakes that can be predicted by electromagnetic signals, such as very low frequency radio waves? None of these topics are things that I learned about at university, but that was 30 plus years ago. So is there any updates on these ideas?
Well, it is yes, no, and no, the answers to those. And yes, so the first question is, yes, we know that small magnitude seismicity and really small magnitude seismicity around 0.5 is triggered with tidal forces. And this is also equal, the tidal forces may be equal to the stresses that they are locally imparted from, let's say, California, from an event happening in China. So and all this are under what the sentence that I spell out at some point in the presentation, that seismologists believe that the Earth crust is always in such delicate balance that even the smallest contribution of stresses from long distance earthquakes or tidal waves might bring some very small faults closer to failure. But it is also important at the same time to keep in our minds that in those cases, the triggered earthquakes, the earthquakes that emerge as a result, are small in magnitude. They're not large magnitude earthquakes. So there is no reason to worry about whether the tides will bring the next magnitude 9. Now, the second question was regarding electromagnetic.
Yes, electromagnetic fields. I think low magnetic fields is what he was saying.
So this is, this is science. Sometimes is like fashion. I mean, we lived those beliefs in the 80s, and it seems now they're recirculating and they're coming back, and we're hearing a lot about this. So the problem with electromagnetic signals or electric or all those kinds of signals that some people believe that they can give us information about a big earthquake coming, they all suffer something we call statistical significance. And also very often, people that believe in those ideas, they do not offer the statistical evidence to support their cases, meaning the following. Even if you see for one time an electromagnetic signal and then a big earthquake, this does not actually mean that these two things share a causal link between them. So in order to prove that, science does not really work with singular cases. So you have to prove that this has happened again and prove that above what we say with statistical significance. So if it has happened many times and it is proven in the past, then I think every scientist would take a look, because obviously the aim of science always is to offer information to the broader community. The problem with those instances and those claims is that they're not really properly delivered and they're not proven. Their efficiency is not proven. So I would say I don't believe in that.
Thank you so much for answering those tough questions. I think it's important, and it's been a very informative talk. I just went to the BGS website. You're right. I think there is always earthquakes. That's what I've always been told. There's always earthquakes happening somewhere, right? We live on a very dynamic Earth. The UK the last month of March had about 20 earthquakes, but they're all under 2.0. So you can't really feel them. The closest one to me, I think, was in Yorkshire, and I'm in Oxfordshire, so not very close at all. But thank you so much, Dr. Segou, for such an incredibly informative talk and an update on the tools that seismologists are learning so we can understand earthquakes better and look at the probability for that next big one. But I really appreciate you being with us. And so I want to thank everyone, our audience, for being with us as well. Oh, sorry, thank you.
Thank you for having me today.
It was fantastic. The audience really enjoyed it. And our next EAS Public Talk, I hope you enjoy us, is Giulia Magnarini, who's finishing her PhD at the Department of Earth Sciences at UCL. She's going to talk about mega landslides on Mars, Earth, and Moon, trying to get more of that geophysics side into the Royal Astronomical Society, because we do advocate astronomy, geophysics, and space sciences. Thank you for being with us. It's been an absolute pleasure. And again, thank you, Dr. Segou, for being with us. Bye-bye.